A cosmic city of galaxies hides secrets we are only beginning to understand. The Hercules Cluster, a sprawling metropolis of thousands of galaxies, is a treasure chest of astronomical oddities. By staying until the end, you will journey through 25 of its most profound and unexplained phenomena, each a piece of a larger cosmic puzzle. How can galaxies exist as faint as ghosts, and what creates colossal shock waves frozen in space? The answers redefine our place in the universe. What does it feel like to peer into a mystery millions of light years wide? This invisible architecture is the first and greatest puzzle we encounter. The Hercules Cluster is held together by a force we cannot see. Galaxies within it are whirling around at speeds that should tear the entire structure apart. If only the stars, gas, and dust we observe were present, their combined gravity would be far too weak to keep these galaxies bound together. They would have flung themselves into the cosmic void long ago. Yet the cluster remains a stable metropolis. This discrepancy is the missing mass mystery. Astronomers measure the velocities of individual galaxies, a technique called velocity dispersion, and the numbers are unequivocal. The visible matter accounts for only a small fraction of the gravitational glue. Something else, something massive and dark, must be providing the rest. Further proof comes from a cosmic trick of light known as gravitational lensing. The immense gravity of the cluster warps the fabric of space-time itself, bending the light from even more distant galaxies behind it. By studying the shape and distortion of that background light, scientists can map the cluster's total mass. The map reveals a vast, diffuse halo of matter that emits no light, no radio waves, no X-rays. It interacts only through gravity. This dark matter scaffold, outweighing all the visible stars and gas by a factor of perhaps 10 to 1, is the hidden skeleton upon which the entire Hercules cluster is built. We are left staring at a cosmic city where the buildings are visible, but the ground they stand on remains utterly invisible. Yet within this dark matter scaffold, the cluster holds galaxies that defy every expectation of what a galaxy should look like. They are cosmic phantoms, vast and sprawling yet almost empty. Astronomers call them ultra-diffuse galaxies, and they represent one of the Hercules cluster's most haunting puzzles. Picture a galaxy the size of our own Milky Way, a majestic spiral spanning 100,000 light-years. Now imagine that immense volume contains only 1% of the stars. That is the reality of galaxies like Dragonfly 44, a ghostly resident of Hercules. It is a gauzy, transparent smudge against the darkness, so faint that it was only discovered in recent years by specialized telescopes designed to see extremely low surface brightness. The existence of such objects forces a profound question. How does something so large with so little visible matter hold itself together at all? The gravitational glue provided by its sparse stars is utterly insufficient. Once again, the shadow of dark matter looms large. The only way an ultra-diffuse galaxy can maintain its structure is if it is embedded within an enormously massive halo of dark matter, a cosmic cushion that outweighs its stars by a staggering margin. But how did it get this way? Two compelling and unsettling theories compete. One suggests these are failed galaxies. Billions of years ago, they began to gather gas and dust to form stars, but their internal processes were stillborn. Perhaps supernova explosions blew away their remaining fuel, or the gas simply never cooled and condensed efficiently. They are cosmic embryos that never fully developed. The other theory is more violent. It posits that these galaxies were once normal, but as they plunged into the dense environment of the Hercules cluster, they were brutally stripped. The cluster's immense gravitational tides and the searing heat of the intracluster gas could have ripped away their star-forming material, leaving behind only a skeleton of old stars and a dominant dark matter halo. Both ideas are plausible, yet neither fully solves the enigma. the ultra-diffuse galaxies stand as silent, faint monuments to processes we are still striving to understand, challenging our very definitions of what makes a galaxy alive or dead. These ghostly galaxies are not the only remnants of ancient violence. Deep within the Hercules Cluster, astronomers have detected colossal, faint arcs of energy, invisible to optical telescopes but blazing in the radio spectrum. These are the radio relics, and they are the fossilized shock waves of the cluster's most catastrophic events. Picture the aftermath of a collision so immense it defies earthly scale. Not between two galaxies, but between two entire subclusters of galaxies, each containing hundreds of members and trillions of stars. As these titanic structures fell together and merged billions of years ago, they generated vast tsunamis of energy that raced through the thin, superheated gas filling the space between galaxies. These shock waves, traveling at millions of miles per hour, act like natural particle accelerators. They sweep up stray electrons and fling them to near light speeds. When these ultra-fast electrons spiral along the weak magnetic fields that permeate the cluster, they emit a specific type of radio light called synchrotron radiation. What we see today as a faint, curved radio relic is the lingering glow of that process, a cosmic scar etched across the heavens. The sheer scale is breathtaking. One of these relics in Hercules can stretch for over 1 million light-years, a structure larger than our entire local group of galaxies. Yet for all their grandeur, the relics are shrouded in mystery. The precise trigger for these shocks remains debated. Was it the initial head-on collision of the subclusters, or a later, more complex sloshing of gas within the newly merged giant? The mechanisms that accelerate particles with such staggering efficiency in these diffuse environments are not fully understood. Furthermore, these relics are not static monuments. They are dynamic puzzles. Their shape, brightness, and spectrum hold encoded information about the speed, direction, and power of that ancient merger. By studying them, astronomers are essentially performing cosmic archaeology, reading the faint radio echoes to reconstruct a violence that occurred when our planet was still barren rock. These giant arcs serve as a stark reminder that the serene city of galaxies we see today was forged in a furnace of unimaginable force, and its faintest radio whispers tell the story of that birth. That searing heat between galaxies holds a paradox of its own. While the radio relics are echoes of ancient violence, the space they ripple through is not empty. It is filled with an ocean of superheated gas, so thin it is a better vacuum than any we can create on Earth, yet so vast it contains more normal matter than all the galaxies in the cluster combined. Seen through X-ray telescopes, this intracluster medium glows with an ethereal, million-degree light, and according to all our basic physics, this gas presents a serious problem. It is incredibly dense and hot at the cluster's outer edges, but even hotter and denser at its heart. In such a core, the gas should be radiating away its energy as X-rays at a ferocious rate. As it loses energy, it should cool down, and as it cools, it should condense and flow inward in a relentless river of material, a cooling flow directly into the cluster's central galaxy. This inward torrent of cold gas should be the ultimate fuel, triggering an explosive burst of new star formation, birthing millions of suns every year. The central galaxy should be a blazing, star-forming furnace, but when astronomers look, they see nothing of the sort. The predicted deluge of cold gas is missing. The furious star formation is absent. The cooling has been mysteriously shut off. This is the cooling flow problem. The gas is hot and it is glowing, but it is stubbornly refusing to cool down and rain into the center as it should. Something is reheating it, balancing the energy loss with a precise, invisible hand. The prime suspect is the most powerful engine in the universe, a supermassive black hole residing in that very central galaxy. The theory goes that as a trickle of gas does manage to cool and fall toward the black hole, it powers up colossal jets of energy. These jets, traveling at nearly the speed of light, blast back into the surrounding hot gas like cosmic blowtorches, stirring it, shock heating it, and preventing further cooling. It is a magnificent feedback loop, a self-regulating thermostat where the black hole's own feast prevents a larger banquet. Yet the mystery endures because the balance is too perfect. The heating is not a constant roar, it is a precise whisper, exactly offsetting the cooling across millions of light years. How does the black hole know how much energy to inject? Is it the only source of heat, or are other processes like the sloshing motions from past mergers also playing a role? The cooling flow problem shows us a universe in a delicate, dynamic equilibrium, where the most violent objects are the gentle guardians preventing even greater chaos. This delicate balance is violently disrupted on a smaller scale by a single, spectacular object. At the heart of a galaxy within the Hercules Cluster, a supermassive black hole is firing twin beams of matter and energy into the void. These are relativistic jets, streams of particles traveling at nearly the speed of light, and they should stretch out in perfectly straight lines for hundreds of thousands of light years. Yet in one particular galaxy, astronomers see something profoundly wrong. The jet is not straight, it is sharply bent, as if a cosmic hand has reached out and pushed it aside. The image is startling, a luminous spear of radio light that takes a sudden, dramatic kink. What force in the universe is powerful enough to bend a beam of near-light-speed particles? The culprit is the very ocean of gas we just discussed, the intracluster medium. This galaxy is not sitting still. It is moving at tremendous speed through the cluster's dense, hot atmosphere. Think of it like a speedboat racing across a lake, its wake streaming behind it. Now, imagine that the water of the lake is not placid but a raging, viscous current. That is the environment here. As the galaxy plows through the million-degree gas, the jet streaming from its black hole slams into this intergalactic wind. The immense ram pressure of the intracluster medium acts like a constant, buffeting gale, pushing against the jet and forcing it to curve. It is a cosmic flag flapping in a hurricane. This single, bent jet is a powerful diagnostic tool. The degree of bending tells astronomers about the density and pressure of the hot gas at that exact location. The fact that it is bent so sharply indicates the intracluster medium is far from a uniform soup. It is a dynamic, turbulent fluid with pockets of extreme density. Modeling this precise interaction, however, is a monumental challenge. The physics involves not just fluid dynamics and gravity, but also magnetic fields and the complex behavior of plasma. Scientists must calculate the galaxy's exact velocity, the jet's power, the local gas density, and the magnetic field strength all at once. It is a three-dimensional puzzle where one wrong variable makes the entire model collapse. This bent radio jet is more than a curiosity. It is a local weather vane in a storm of galactic proportions, showing us that the space between galaxies is not a passive void, but an active, shaping force that can redirect the most powerful beams in the cosmos. These jets are bent by the present, but the light we see from Hercules tells a story of the deep past encoded in its color. To map the vast distances of the cosmos, astronomers rely on a fundamental tool called redshift. As a galaxy moves away from us, the light waves it emits are stretched, shifting toward the red end of the spectrum, much like the lowering pitch of a receding siren. The faster it recedes, the greater the redshift, and in an expanding universe, greater redshift generally means greater distance. Within a massive cluster like Hercules, most galaxies share a similar, huge redshift, placing them all at roughly the same cosmic address, billions of light years away. Their individual motions are tiny compared to this universal flight, yet here lies a subtle puzzle. When scientists measure with extreme precision, they find that not all galaxies in Hercules are in lockstep. A few show slight but significant deviations, their redshifts a fraction higher or lower than the cluster's average. These are redshift anomalies, and they hint at peculiar motions within the city. One explanation is sheer velocity. A galaxy could be a recent arrival, falling into the cluster for the first time at a blistering speed, its motion either toward us or away from us superimposing a small shift on the dominant cosmic expansion. Alternatively, it might have undergone a close gravitational encounter with another massive galaxy, a cosmic slingshot that sent it careening on a wild trajectory through the cluster's core. But there are more intriguing possibilities. The cluster's own immense gravity creates a complex landscape of tides and potentials. A galaxy might be tracing a long, looping orbit within this invisible well, its speed varying along its path. Or the anomalies could point to something more structural, like small subgroups of galaxies that have not yet fully mixed with the main population, each with its own slight dynamical history. There is also the ever-present challenge of measurement, distinguishing the true motion of a galaxy from effects caused by the swirling of its own stars, or from subtle quirks in the instruments themselves, requires extraordinary care. Each anomalous redshift is a small clue, a single thread in the dynamic tapestry of the cluster. By untangling them, astronomers can begin to reconstruct the traffic patterns of this galactic metropolis, revealing which galaxies are settled residents and which are speeding newcomers on chaotic paths through the dark. The redshift of a galaxy tells us where it is, but the objects within it can tell a far stranger story. In the heart of one seemingly ordinary galaxy within Hercules, astronomers found a supermassive black hole of staggering proportions. This is not just a large black hole, it is an overmassive one, a behemoth whose weight defies all expectation. Current models of galactic evolution suggest that black holes and their host galaxies grow together in a kind of cosmic symbiosis. The size of the central black hole is typically proportional to the mass of the galaxy's central bulge of stars, but this Hercules galaxy breaks that rule completely. Its black hole is monstrously oversized, containing a mass that should belong to a galaxy 10 times larger. How does a galaxy of modest stature come to host such a gravitational titan? The possibilities are as thrilling as they are unsettling. Perhaps this black hole had a head start, forming from the direct collapse of a gigantic cloud of primordial gas in the universe's infancy, becoming a giant seed before its galaxy even properly assembled around it. Or maybe it achieved its size through a different, more violent path. This galaxy could be the stripped-down remnant of a much larger one that was torn apart during a past merger, its outer stars scattered into the cluster, leaving behind only its dense core and its now overmassive black hole as a ghost of its former self. This single object challenges the textbook story of co-evolution, forcing us to consider that black holes and their galaxies might not always grow in lockstep, and that the history written in their relative sizes can be one of shocking imbalance. While one galaxy hides an oversized secret, another is being violently unmasked. Elsewhere in the cluster, a beautiful spiral galaxy is undergoing a public and brutal transformation. As it speeds through the dense intracluster medium, it faces a hurricane-force headwind of superheated gas. This is ram pressure stripping in action, and it is as dramatic as it sounds. The galaxy's own interstellar gas, the raw fuel for future stars, is being violently ripped away by the sheer force of its motion through the cluster's atmosphere. What remains is a spectacle astronomers call a jellyfish galaxy. You can still see the galaxy's original spiral disk, but streaming out behind it, like luminous tentacles or a cosmic wake, are long, trailing tendrils of gas. Within these tendrils, something miraculous and desperate is happening. The gas, compressed and shocked as it is torn free, is collapsing to form new stars. These are stars born in exile, flickering to life not within the safety of the galactic disk, but in the turbulent streams of material being left behind. This galaxy is caught in a single, frozen moment of metamorphosis. It is a spiral being turned into a lifeless elliptical, its star-forming fuel stolen, its future shut down. The process reveals the profound environmental effects within a cluster. It is not a gentle place. The space between galaxies is a punishing medium that can dictate a galaxy's very fate, reshaping its structure and ultimately determining whether it will continue to give birth to new suns or fade into a red and dead retirement. Watching this event unfold is like witnessing the slow-motion predation of a cosmic ecosystem, where the environment itself is the predator. That solitary giant elliptical galaxy may be a cosmic tyrant that has finished its conquest. Astronomers call such a system a fossil group, and finding one in the Hercules Cluster would be a profound discovery. The theory is both elegant and brutal. In the early universe, a small group of perhaps a dozen large galaxies fell together by gravity. Within this crowded neighborhood, the most massive galaxy, driven by its superior gravity, began a slow feast. Over billions of years, through a series of mergers and close encounters, it consumed all of its major rival galaxies. What remains today is a single, dominant elliptical galaxy, surrounded only by a retinue of tiny, faint satellite galaxies, the cosmic equivalent of a king who has devoured all the other nobles, leaving only servants. The evidence for this lies in the X-ray glow. When large galaxies merge, their hot gas halos combine, creating an immense spherical atmosphere of million-degree plasma. A true fossil group should sit at the heart of a surprisingly large and relaxed X-ray halo, a sign of a long, stable reign with no recent major disruptions. Hercules may contain a candidate for such an object, a solitary giant whose X-ray aura hints at a violent past now settled into quiet dominance. It is a snapshot of galactic evolution taken to its ultimate, lonely conclusion. But the debris from that ancient feasting does not simply vanish. It contributes to a ghostly sea of stars that fills the entire cluster, a phenomenon known as intracluster light. This is not the light of galaxies. It is a faint, diffuse glow from billions of stars that have been torn from their home galaxies and now drift freely in the gravitational well of the cluster itself. To see it is an immense challenge, requiring telescopes to stare at a patch of seemingly empty sky and subtract the light from every known galaxy and star, revealing the whisper that remains. This light is the cosmic evidence of the cluster's violent history. Every galaxy collision, every close gravitational encounter, every instance of tidal stripping flings stars out into intergalactic space. These stars are no longer bound to any single galaxy. They are citizens of the cluster as a whole, tracing elongated orbits through the dark. Mapping this faint glow is like reconstructing a crime scene from scattered dust. The pattern and color of the intracluster light can tell us which galaxies were the major contributors to this stellar haze and when the most violent stripping events occurred. The sheer amount of this light is staggering. In some clusters, it can account for up to half of all the stars. In Hercules, this diffuse sea represents the integrated history of every merger, every cannibalization, every act of violence that has shaped the galactic metropolis. It is the cluster's memory, written in the faintest possible light, a permanent record of the chaos that built the ordered structure we see today. This faint sea of exiled stars is a testament to the immense forces at play, forces that can also act as a cosmic catapult. Drifting through this stellar haze is a galaxy moving at a breakneck pace, a high-velocity rebel that seems intent on escaping the cluster itself. Its speed, measured relative to the calm average of its neighbors, is far too great to be a simple orbital motion. This galaxy is a runaway, and its existence demands an explanation. Where did it get such incredible kinetic energy? The most likely scenario is a violent gravitational slingshot. Picture a close encounter between three galaxies. As two of them swing around each other, a third, smaller galaxy can be flung out at tremendous speed like a stone from a sling. This galaxy may have been the unfortunate projectile in such a three-body interaction, ejected from the dense core of the cluster and now on a one-way trip into the intercluster void. Alternatively, it could be an intruder, a galaxy from outside the cluster that is falling in for the very first time, accelerated to a phenomenal velocity by the cluster's immense gravitational pull. Determining its true origin is a detective story written in velocity and trajectory. If it is being ejected, studying its path could point back to the location of the ancient encounter that launched it. If it is an infalling newcomer, its composition might differ from the long-term residents. This high-velocity galaxy is a reminder that the cluster is not a static sculpture, but a dynamic ballet where gravitational forces can fling entire star systems across millions of light-years. While one object races away, another sits perfectly still, pouring out a mysterious torrent of energy. Elsewhere in the cluster, X-ray telescopes have pinpointed a brilliantly intense source. It is point-like, meaning it originates from a region no larger than a single star system, yet it outshines the combined X-ray output of 1,000,000 suns. This is an unidentified X-ray source, a beacon with no clear face. In visible light, that same spot appears empty or shows only a faint, unremarkable smudge. So what is it? Astronomers have a few compelling suspects. The first is a quasar, a phenomenally bright active galactic nucleus powered by a supermassive black hole, but one that lies far behind the Hercules Cluster. The cluster itself would act as a lens, magnifying the quasar's X-ray light and making it appear as a brilliant, isolated point. The second suspect is something called an ultra-luminous X-ray source, or ULX. These are typically stellar mass black holes or neutron stars that are feeding at an impossibly high rate, somehow violating their theoretical limits and glowing with extraordinary intensity. The third and most tantalizing possibility is an intermediate mass black hole. This would be a cosmic missing link, a black hole with a mass thousands of times that of our Sun, bridging the gap between small stellar remnants and the supermassive giants at galactic centers. Such an object, if it is wandering alone in intracluster space or hiding in a small, faint galaxy, could produce exactly this kind of fierce, localized X-ray flare. Each explanation points to a different and extraordinary phenomenon. The unidentified source remains a label on a map, a question mark of pure energy challenging us to look deeper and uncover the powerful engine hidden within the cluster's glow. The brilliant X-ray point source is a beacon of concentrated power, but the broader population of the cluster reveals a puzzling absence. Where are all the small galaxies? According to our most sophisticated supercomputer simulations of cosmic structure formation, a giant cluster like Hercules should be teeming with thousands of dwarf galaxies, small, faint satellites orbiting the larger members like moths around a street lamp. Yet when astronomers count, the numbers fall short. This is the dwarf galaxy deficiency, the cluster-scale version of the famous missing satellite problem observed around our own Milky Way. The simulations, which trace the growth of dark matter halos from the early universe to the present, predict a rich hierarchy of structures. Small halos form first, and many should survive to become dwarf galaxies. Their relative scarcity in Hercules suggests something is systematically destroying or hiding them. One compelling answer is environmental destruction. The cluster is a hazardous place for fragile dwarfs. As they orbit through the dense core, they face relentless ram pressure stripping that can blow away their gas, and even more effectively, tidal stripping from the immense gravity of giant galaxies can tear them apart entirely, their stars adding to the diffuse intracluster light. They may be getting devoured, digested before we can ever see them. Another possibility is that many dark matter halos simply never lit up with stars. Perhaps the ultraviolet radiation from the first galaxies, a process called reionization, heated the gas in the smallest halos so they could never cool and form stars, leaving them as dark, invisible ghosts. The deficiency forces us to question whether our simulations overpredict small structures, or if our telescopes are still not sensitive enough to detect the faintest, most diffuse dwarfs hiding in the cluster's glare. It is a census with missing persons, and each missing dwarf galaxy is a clue to the violent environmental processes that shape galactic populations. While we count galaxies, we can also take a chemical census of the space between them. That superheated intracluster gas is not pristine. It is a polluted soup enriched with heavy elements forged in the hearts of stars and scattered by violent explosions. By analyzing the specific X-ray fingerprints of this gas, astronomers can measure the abundance of elements like iron, oxygen, and magnesium. These ratios are a historical record, a chemical imprint of the cluster's entire star-forming past. And here, Hercules presents another puzzle, a chemical imbalance. The patterns do not always match our expectations. Iron is plentiful, as expected from the long-term pollution by Type I, a supernova, the thermonuclear explosions of white dwarf stars. But the amounts of lighter elements like oxygen and magnesium, which are primarily produced in the core collapse supernova of massive, short-lived stars, show anomalies. The ratios suggest the early star formation in the cluster's galaxies was either more intense, more efficient, or involved different types of stars than we see in our cosmic neighborhood. Perhaps the first generations of stars in these galaxies were predominantly very massive, exploding quickly and seeding the protocluster gas with a specific blend of elements. Or the timing of the enrichment was crucial. If the cluster assembled very early and rapidly, the blast waves from countless core collapse supernova might have mixed the elements into the intracluster medium more effectively before later generations of Type I, a supernova, added their iron. Reading this chemical record is like analyzing layers of sediment in a fossil bed. Each element ratio is a stratum telling us about the climate of star formation billions of years ago. The imbalance challenges simple models and hints at a more complex, more explosive youth for the galaxies of Hercules, where the very ingredients of planets and life were forged and scattered in proportions we are still learning to decode. That chemical record is written in light bent by the cluster's immense gravity. Among the faint glow of Hercules, astronomers sometimes find something astonishing. Thin, graceful arcs of blue light curved like celestial smiles against the darker background. These are not structures within the cluster itself. They are gravitational lens arcs, the distorted and magnified images of galaxies that lie far, far behind the Hercules cluster. This is Einstein's theory of general relativity made visible. The combined mass of the cluster, all its visible galaxies, hot gas, and most importantly, its enormous dark matter halo, warps the fabric of space-time around it. When light from a distant background galaxy travels through this warped region, its path is bent, much like light passing through a giant, lumpy lens made of pure gravity. If the alignment is perfect, the background galaxy's image can be stretched and duplicated into these spectacular arcs, or even into multiple, separate images of the same object. These arcs are more than just beautiful oddities, they are precision tools. By meticulously measuring the distortion, how stretched the arc is, how bright, its exact shape, scientists can perform a kind of cosmic tomography. They can map the total mass distribution of the cluster in 3 dimensions, pinpointing where the dark matter is most densely concentrated. It is a direct way to weigh the invisible, using the distorted light of the distant universe as our scale. While lensing reveals mass through bent light, another faint signal reveals a sea of high-energy particles. Enveloping the entire Hercules cluster is a vast, amorphous cloud of radio emission known as a radio halo. Unlike the sharp, curved radio relics that mark ancient shock waves, this halo is a diffuse, almost ghostly glow that permeates the cluster's core. It tells us that the space between galaxies is not empty, but filled with a sea of relativistic electrons, particles whipped up to nearly the speed of light. These electrons spiral along the cluster's weak magnetic fields, emitting the synchrotron radio waves we detect. The central mystery is how these electrons became so energized in the first place. They require a colossal, cluster-wide injection of power. The leading theory points directly to the cluster's violent origin. During the massive merger that formed Hercules, the turbulent sloshing and collisions of gas would have generated shock waves and turbulence throughout the entire core. This chaos could have continuously accelerated electrons over vast volumes, like a cosmic blender churning particles to extreme speeds. However, the details are hotly debated. The turbulence alone may not be efficient enough to explain the halo's brightness and extent. Some models suggest that protons are also accelerated and then collide with other particles, generating the electrons we see. Others propose that existing populations of fast electrons from galaxies and supernova are re-accelerated by the merger's turbulence. The diffuse radio halo is the lingering echo of the cluster's most traumatic birth pangs, a signature of energy that has suffused the entire system. Yet the exact engine that charged this vast sea of particles remains one of Hercules' most pervasive puzzles. The diffuse radio halo is a signature of the cluster's violent birth, but some of the most dramatic evidence of that violence is locked in objects that are surprisingly small. Scattered throughout the Hercules cluster are tiny, brilliant points of light that at first glance look like simple star clusters, but their light tells a different story. These are ultra-compact dwarf galaxies, and they are cosmic anomalies. They pack tens of millions of stars into a sphere only about 200 light-years across. If you placed one at the location of our Sun, its outer edge would only reach a quarter of the way to our nearest stellar neighbor, yet it would contain a stellar density so extreme the night sky would be a perpetual blazing twilight. Their very existence is a puzzle. Are they simply the most massive globular clusters ever formed, or are they something far more dramatic than naked, surviving hearts of galaxies that have been completely stripped apart? This second possibility is chilling. A small galaxy, perhaps a dwarf elliptical, falls into the cluster and ventures too close to a giant. The immense tidal forces of the larger galaxy act like a cosmic cheese grater, peeling away the outer layers of stars over billions of years. What remains is the dense, nigh indestructible nucleus, an ultra-compact dwarf, now orbiting as a trophy of that ancient act of cannibalism. Their ambiguous nature makes them crucial fossils. By studying their chemical composition and age, astronomers can try to discern their origin. Do their stars show the enriched metals of a complex galactic history, or the simpler signature of a single burst of star formation in a cluster? Each UCD is a tiny, dense clue to a much larger story of destruction. That story of destruction is written on a far grander scale in the faintest light of all. Stretching between the galaxies of Hercules, like cosmic scars not yet healed, are vast, tenuous rivers of stars known as tidal streams. These are not bound galaxies, but the lingering debris from past encounters, the stars that were flung out during collisions and close passes, now tracing long, graceful arcs through the gravitational well of the cluster. To see them requires pushing telescopes to their absolute limits, filtering out every other source of light to reveal these ghostly contrails against the darkness. Each stream is a historical document. Its shape, length, and the motion of its stars encode the details of the event that created it. By mapping these streams, astronomers can perform celestial forensics. A long, thin stream suggests a slow, grinding disruption of a small galaxy over billions of years. A broader, more diffuse fan might point to a single, catastrophic collision. Following the stream's path can even lead back to both the perpetrator and the victim, the large galaxy that did the stripping and the faint, surviving core of the dwarf that was consumed. These stellar rivers are the visible evidence of the hierarchical growth that built the cluster. They show that the giant elliptical galaxies we see today were not born that way. They were assembled through a relentless process of merging and accretion. The tidal streams are the glittering dust left behind from that construction, allowing us to rewind time and watch in slow motion as the cluster's largest galaxies grew fat on their neighbors. In their faint glow, we see the ongoing digestion of the cosmic city, a reminder that even now, the metropolis of Hercules is still being shaped by its violent past. These ghostly stellar rivers show a cluster still digesting its past, but the most powerful force shaping its present is a cycle of violence and silence at the very center. This is the GN feedback cycle, a cosmic heartbeat that regulates the life of the entire cluster. An active galactic nucleus, the supermassive black hole at the core of the central galaxy, does not feed constantly. It cycles between dormancy and eruption in a self-regulating loop. Here is how it works. As hot gas from the intracluster medium slowly cools, it begins to drizzle toward the center, funneling toward the black hole. This incoming fuel spins up an accretion disk, a whirlpool of superheated matter, and powers up the black hole's engine. The black hole responds by launching those tremendous relativistic jets and sending out powerful blasts of radiation. This outburst acts like a cosmic pressure washer, pumping energy back into the surrounding gas, reheating it and pushing it away. The cooling flow is halted. With its fuel supply now cut off, the black hole's activity subsides and it goes quiet. Then, over millions of years, the hot gas once again begins to radiate away its heat and cool. The drizzle resumes and the cycle starts anew. It is a perfect self-correcting thermostat. The profound mystery is the trigger mechanism. What is the precise signal that tells the black hole to switch on? Is it a specific rate of gas inflow? Does it involve magnetic fields building up to a breaking point within the accretion disk? Or are there external triggers like a smaller galaxy falling in and stirring up the central gas, providing a sudden buffet for the black hole? The cycle's regularity is also puzzling. Observations suggest these outbursts happen every few 100 million years, but we do not understand what sets this cosmic clock. This feedback cycle is the dominant force preventing the cluster's core from collapsing into a starburst, and its elegant, brutal rhythm is what keeps the entire metropolis in balance. While this cycle governs the present, the cluster's long-term transformation is etched in the color of its galactic population. This brings us to the Butcher-Ohmler effect, a discovery that fundamentally changed how we see clusters evolve. In the 1980s, astronomers Harvey Butcher and Augustus Ohmler made a startling observation. When they looked at very distant clusters, meaning clusters as they were billions of years in the past, they found a surprising abundance of blue, spiral galaxies actively forming stars. This was in stark contrast to nearby clusters like Hercules today, which are dominated by red, dead elliptical galaxies where star formation has long since ceased. The effect is clear. Clusters in the past were blue and lively. Clusters in the present are red and quiet. This poses a monumental question. What happened in the intervening billions of years to transform these vibrant spiral cities into graveyards of red giants? The answer lies in the cluster environment itself, a recipe for galactic sterilization with several key ingredients. First is ram pressure stripping, the process we saw creating jellyfish galaxies, which violently removes the cold gas needed to form new stars. Second is galaxy harassment, the cumulative effect of many fast, close gravitational encounters that disrupt a spiral's delicate structure, puffing it up into a featureless elliptical. Third is the exhaustion of fuel, as a galaxy simply uses up its available gas and, cut off from fresh supplies by the hostile intracluster environment, cannot make more. The Butcher-Ohmler effect is not just a change in color, it is a change in state. It shows us that the cluster is a giant evolutionary pressure cooker. Galaxies that enter it as blue, star-forming spirals are, over cosmic time, processed and transformed into red, passive ellipticals. The mystery within this effect is one of timing and efficiency. Did this transformation happen rapidly during major cluster mergers, or was it a slow, steady process over eons? Why did some spirals survive longer than others? The effect forces us to see Hercules not as a static collection of islands, but as a dynamic ecosystem where the environment dictates the very fate of its galactic inhabitants, painting them from blue to red across the canvas of cosmic time. The red and quiet galaxies of Hercules tell one story, but the very fabric of space around them tells another, written in the universe's oldest light. This is the Sunyaev-Zeldovich effect, a subtle but powerful tool. The entire cosmos is bathed in the cosmic microwave background, the cooled remnant glow from the Big Bang itself. As this ancient light passes through the Hercules cluster on its way to us, it encounters that ocean of superheated electrons in the intracluster gas. Some of these photons collide with the fast-moving electrons, gaining a tiny boost of energy. This interaction imprints a specific cold shadow on the background radiation at certain radio wavelengths. The depth of this shadow is directly proportional to the pressure of the gas, which in turn tells us the cluster's total mass. It is a beautifully independent measurement, a cosmic scale that does not rely on visible light or galaxy motions. Yet here a discrepancy arises. When scientists compare the mass derived from the Sunyaev-Zeldovich effect with the mass calculated from gravitational lensing or the motions of galaxies in Hercules, the numbers do not always align perfectly. This is a measurement mystery with profound implications. Is the intracluster gas not as smoothly distributed as our models assume? Could there be unseen clumps or bubbles of very hot or very cool gas altering the pressure profile? Or does the discrepancy point to something more fundamental, perhaps a subtle flaw in how we connect gas pressure to total mass in such a complex, merging environment? Each method is measuring a slightly different aspect of the cluster's reality, and their disagreement is not a failure but a clue. It forces us to refine our three-dimensional picture of this galactic city, reminding us that even our most elegant cosmic measurements must be cross-checked against the stubborn, detailed truth of observation. While the Sunyaev-Zeldovich effect is a permanent, faint imprint, the cluster may also be the source of the universe's most brilliant and fleeting flashes. Fast radio bursts are among the most enigmatic phenomena in modern astronomy. These are bursts of radio waves that last mere milliseconds, yet in that blink of an eye they release as much energy as our sun does in 80 years. Their origins have been a frantic puzzle, with suspects ranging from magnetars, which are highly magnetized neutron stars, to exotic theories involving cosmic strings or even advanced civilizations. Could a dense environment like the Hercules cluster be a breeding ground for these events? The intense gravitational forces and frequent interactions provide a compelling backdrop. One leading progenitor candidate is the magnetar. Imagine a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, a field so intense it can literally crack the star's crust, releasing catastrophic bursts of energy. Such objects could form in the aftermath of supernova within the cluster's galaxies. The dense environment might even produce them more frequently. Furthermore, the chaotic interactions within Hercules could create the perfect conditions for other potential burst sources. A close encounter or merger between two neutron stars could produce a short, colossal blast of radio waves as they finally spiral together. Or a neutron star orbiting a supermassive black hole might experience tremendous tidal forces at its closest approach, sparking a burst. While no fast radio burst has been definitively pinned to Hercules yet, the cluster's nature makes it a prime hunting ground. Its galaxies are cosmic petri dishes for the violent stellar evolution that could create these extreme objects, and its vast volume means it likely hosts many of them. The search continues, with radio telescopes scanning the skies, hoping to catch a millisecond flash from this galactic metropolis that could finally unlock the secret of where these mysterious cosmic sirens call home. The search for millisecond flashes leads us back to the cluster's enduring structural mysteries, beginning with a debate over its very heart. The cool core controversy centers on a simple but critical question. Is the center of the Hercules cluster calm and settled, or is it still churning from ancient violence? A classic relaxed cluster possesses a cool core. Here, the dense gas at the very center has had time to radiate away its heat, creating a steep temperature gradient from a hot outer envelope down to a significantly cooler, dense inner region. This is the sign of a mature, undisturbed system. However, many observations suggest Hercules tells a different story. Its central gas appears warmer and more disturbed, lacking that sharp temperature drop. This points to a non-cool core or a warm core state. The implication is dramatic. It suggests that the colossal merger which formed Hercules was so recent and so violent that it stirred up the central gas like a spoon in a cosmic cup, redistributing the heat and preventing a cool core from re-establishing itself. The controversy lies in the details. Some studies detect subtle signs of cooler gas, perhaps a fledgling cool core trying to reform. Others see only the uniform heat of a thoroughly mixed system. This isn't just academic, it's a forensic timeline. Determining the state of the core helps pin down exactly when the cluster's last major merger occurred, telling us whether we are looking at a system that has settled into equilibrium or one that is still ringing like a struck bell from a collision billions of years ago. This structural debate extends from the hot gas to the very orientation of the galaxies swimming within it. Scattered across the vast volume of Hercules, galaxies might not be pointing in random directions. There are tantalizing hints of a large-scale galaxy alignment, a subtle cosmic patterning where the shapes or spins of galaxies, or even the arrangements of their satellite dwarf galaxies, show a preferred orientation relative to the cluster's center or to other galaxies. This is a profoundly strange idea. Why would an island universe care which way it points? The leading theory points to the cluster's immense tidal field. As galaxies fall into the cluster, they experience stretching forces from the cluster's overall gravity. These tidal forces can gradually torque a galaxy, aligning its elongated shape or influencing the plane in which its satellites orbit. It's a slow, cosmic process of orientation by the environment's invisible hand. An even more intriguing possibility reaches back to the beginning. These alignments might be primordial, fossils from the conditions of the universe when these galaxies first formed. If galaxies condensed from vast sheets or filaments of dark matter and gas in the early cosmos, they might have inherited a spin direction aligned with that original cosmic web. Finding such patterns in Hercules would be like discovering that all the buildings in a city are subtly tilted in the same direction because they were built on the slope of an ancient, buried hill. Confirming these alignments is incredibly difficult, requiring precise measurements of thousands of galaxies. But if real, they would reveal that the cluster's influence isn't just about destroying gas or triggering mergers. It's a subtle sculptor that can dictate which way a galaxy faces on the grandest of stages. The alignments of galaxies may be subtle clues to ancient history, but they also point toward a future written in the motion of the entire structure itself. The ultimate fate of the Hercules cluster is not to remain an island. It is a traveler on the largest map of all, the cosmic web, and its journey is just beginning. This sprawling metropolis of galaxies is not isolated. It is a major node within an even grander architecture, bound by gravity to other clusters and filaments in a dance that will last for eons. Current observations and sophisticated simulations suggest Hercules is on a slow-motion collision course with its immense neighbor, the Corona Borealis supercluster. This is not a merger of galaxies, but a merger of entire galactic metropolises, over tens of billions of years drawn together by their mutual gravitational pull. These two titanic structures will fall toward one another. The resulting collision will be an event of almost unimaginable scale, a replay of the ancient mergers that built Hercules but magnified 1,000-fold. It will generate shock waves that make the current radio relics seem like gentle ripples, violently reheating the combined gas of both clusters to temperatures we can scarcely model. The chaotic interplay of dark matter halos will fling galaxies on wild, high-velocity orbits, creating a storm of tidal streams and likely destroying countless fragile dwarf systems in the process. The central black holes of the largest galaxies may eventually find each other, sinking to the new common center through gravitational waves and merging in an event that would shake the fabric of space-time. This future megacluster, a gravitational titan containing many thousands of galaxies, could become one of the largest bound structures in the entire observable universe. Yet even this colossal entity will not be the end of the story. In a universe dominated by dark energy, the accelerating expansion of space will eventually isolate such superclusters from one another. Over trillions of years, the galaxies within this giant will slowly exhaust their fuel. One by one, their stars will burn out and the lights will go out. The cluster's fate, then, is a magnificent crescendo followed by an unimaginably long, quiet fade. Every phenomenon we have explored, from the dark matter scaffold and the ghostly ultra-diffuse galaxies to the bent jets and the reddened stellar populations, is merely a single frame in this epic film. The Hercules Cluster is not a static museum piece. It is a living, breathing, violently evolving entity, and we are privileged to witness but a single, fleeting moment in its multi-billion-year biography. That hidden scaffold of dark matter is more than just a placeholder in our equations. The hunt for its true identity is one of the most profound quests in modern science. What could this invisible substance, which outweighs all normal matter 5 to 1, actually be? Scientists have proposed several compelling candidates, each stranger than the last. The leading contender for decades has been the WIMP, or weakly interacting massive particle. As the name suggests, these are hypothetical particles that are massive compared to particles like electrons, and they interact with normal matter only through gravity and the weak nuclear force, the same force behind radioactive decay. This extreme shyness is why they have so far evaded direct detection. Another fascinating candidate is the Action, a particle originally proposed to solve a different puzzle in particle physics. Actions would be incredibly light, potentially billions of times lighter than an electron, but they would exist in such staggering numbers that they could still account for the dark matter. Their behavior would be more wave-like than particle-like, forming a diffuse, quantum fog permeating the cosmos. There are even more exotic ideas like sterile neutrinos or primordial black holes formed in the universe's first moments. The search is a multi-front war. Deep underground, in abandoned mines and beneath mountains, experiments like LUX Zeppelin and Xeno NNT use vats of ultra-pure liquid xenon. They wait in profound silence and darkness, hoping that a single, elusive WIMP will, on very rare occasion, bump into the nucleus of a xenon atom, producing a tiny flash of light and a pulse of charge that sensitive instruments could catch. Other experiments hunt for actions by using powerful magnetic fields to try and convert them into detectable photons. Yet for all this ingenuity, space itself remains the ultimate laboratory. This is where a colossal structure like the Hercules Cluster becomes indispensable. We cannot recreate its scale or its gravitational forces anywhere on Earth. By observing how the cluster's gravity bends light from distant galaxies, creating those gravitational lens arcs, we map the dark matter's distribution with precision. By measuring the velocities of galaxies whirling within the cluster, we weigh the dark matter halo. By studying how dark matter guides the formation of structure, from the largest filaments of the cosmic web down to the strange survival of ultra-diffuse galaxies, we learn about its properties. Does it interact with itself? Does it have any internal structure, or is it perfectly smooth? The cluster's behavior under the stress of massive mergers provides clues that no underground detector can match. Every unexplained phenomenon we see in Hercules, from the missing dwarf galaxies to the precise shape of radio relics, is a piece of evidence in the dark matter trial. While experiments on Earth listen for a whisper, we are watching the dark matter shout its influence across millions of light years, sculpting a metropolis of galaxies we can only understand by first deciphering the shadow that holds it all together. Those faint radio arcs are cosmic scars, but their exact story is locked in a violent past we can only access through digital reconstruction. To understand how a shock wave a million light-years long could freeze in the darkness, cosmologists turn to the most powerful tools ever built, not telescopes but supercomputers. They feed these machines with the fundamental laws of physics, gravity, hydrodynamics, electromagnetism, and set them a monumental task: simulate the birth of the Hercules Cluster. The starting point is two vast subclusters, each a swirling metropolis of hundreds of galaxies embedded in its own colossal halo of dark matter and a seething ocean of hot gas. The simulation begins. Drawn together by their immense mutual gravity, these titans fall toward each other across hundreds of millions of years. They do not collide head-on like simple billiard balls, but engage in a complex spiraling dance. As their dark matter halos first interpenetrate, they begin to stir the gas. Then comes the moment of impact. The dense cores of hot gas from each subcluster slam together. This is not a solid impact, but a fluid one, like two weather fronts colliding in a planetary atmosphere, but on a scale that defies comprehension. The collision generates vast tsunamis of energy, shock waves that race outward through the thin, magnetized plasma at speeds exceeding 1,000,000 miles per hour. In the simulation, these shocks appear as sharp, spherical fronts of intense pressure expanding into the surrounding medium. This is where the real magic and the real challenge begins. The shock waves themselves are not what we see as radio relics. We see the aftermath. The simulations must now model how these moving walls of compressed gas and magnetic fields act as natural particle accelerators. They sweep up stray electrons that already float in the intracluster plasma. Through a process called diffusive shock acceleration, these electrons get trapped, bouncing back and forth across the shock front, gaining a little more energy with each crossing until they are hurled to near light speeds. Finally, the simulation must calculate what happens next. These ultra-energetic electrons then spiral along the faint magnetic field lines that are woven through the cluster, and in doing so, they emit synchrotron radiation, the specific type of radio light that our telescopes finally detect. The computer's final output is a synthetic radio map, a prediction of what the relic should look like, and this is where the mystery deepens. Getting the simulation to produce a relic that matches the exact shape, brightness, and spectrum of the real structures in Hercules is incredibly difficult. The observed relics are often thin, sharp, and intensely bright on one edge. Reproducing that requires a perfect, nearly head-on collision with just the right impact parameter. The magnetic fields, which are poorly understood on these scales, must be amplified and aligned in very specific ways by the shock to produce the observed radio intensity. Even the precise efficiency of the particle acceleration is a major unknown. If it is too high or too low, the simulated relic will be far too bright or too faint. Each failed simulation is not a defeat but a clue. It tells scientists that their assumptions about the merger's angle, speed, or the state of the primordial magnetic fields might be wrong. They tweak the initial conditions and run the simulation again, a process that can take weeks on thousands of computer processors. The goal is a digital recreation so precise it becomes a time machine, allowing us to witness the exact moment, billions of years ago, when the Hercules Cluster screamed its birth into the silent radio sky. The monstrous black hole hidden within a modest galaxy challenges a cosmic rule we thought was universal. For decades, astronomers have observed a tight and elegant correlation between a supermassive black hole and its home. The mass of the central black hole is almost always proportional to the mass of the galaxy's central bulge, the dense spherical swarm of older stars at its core. It is a scaling relation, a predictable partnership that suggests these two titans grew together across cosmic time, locked in a gravitational symbiosis. The black hole feeds on infalling gas, but its own energetic outbursts regulate that feeding, influencing how many stars form in the bulge. It is a beautiful, balanced dance. Then we look at Hercules. One particular galaxy, a seemingly unremarkable member of the cluster, shatters this harmony. Its central bulge is of a certain moderate size, implying a black hole of perhaps a few 100 million solar masses. Yet measurements reveal a behemoth, a black hole tipping the scales at several billion solar masses. This is not just a slight discrepancy, it is an order of magnitude violation, an overmassive black hole that has completely outgrown its galactic home. How did this happen? How does a black hole become a giant in a city of ordinary proportions? One theory points to a history of relentless cannibalism. This galaxy may have been the victor in a series of galactic mergers within the dense cluster environment. Each time it consumed a smaller neighbor, it not only added stars to its outer halo, but also funneled the victim's central black hole toward its core. Over time, multiple black holes could have spiraled together and merged, creating a single composite monster whose mass reflects a violent lineage of conquests, not a peaceful co-evolution with its current stellar bulge. The galaxy's visible structure today would be just the latest version, while its black hole carries the combined weight of many destroyed galaxies. Another, even more intriguing possibility reaches back to the universe's infancy. In the chaotic early cosmos, long before the Hercules Cluster fully assembled, this galaxy may have been blessed with a unique fuel supply. Vast rivers of cold, dense gas flowing along the filaments of the cosmic web could have funneled directly into its core. This provided a pure, intense feast for the budding black hole, allowing it to grow rapidly in a short period, perhaps even before its host galaxy had built up a substantial bulge through normal star formation. It bypassed the usual partnership, becoming obese on a diet of primordial fuel while its stellar home was still under construction. This outlier in Hercules forces us to reconsider the rulebook. It shows us that while scaling relations describe a common path, they are not destiny. In the extreme environment of a massive cluster, where mergers are frequent and ancient conditions varied, black holes can write their own violent, exceptional histories, leaving behind these cosmic anomalies as evidence of a much more unruly past. That overmassive black hole is a singular anomaly, but the dwarf galaxy deficiency is a widespread pattern, a census problem that reaches into the dark heart of the cosmos itself. The missing dwarfs of Hercules are not just absent, they are a direct challenge to our understanding of the universe's most abundant ingredient. Our most successful cosmological model, called lambda cold dark matter, paints a very specific picture of how structure forms. In this model, dark matter is cold, meaning its particles move slowly compared to the speed of light from the universe's earliest moments. This slowness allows it to clump together easily, starting with the tiniest seeds. Billions of years of gravitational growth should result in a cosmic hierarchy, a few enormous halos hosting giant clusters like Hercules, and a vast, swarming population of smaller dark matter halos, each a potential home for a dwarf galaxy. The supercomputer simulations are unequivocal. Hercules should be orbited by thousands of these faint satellites. Their scarcity is therefore a glaring clue. One straightforward explanation is that galaxy formation is simply inefficient on the smallest scales. Perhaps the vast majority of those predicted small dark matter halos gathered gas in the early universe, but that gas was heated by the intense ultraviolet light from the first giant galaxies, a process called reionization. This heating prevented the gas from cooling and collapsing to form stars, leaving the halos dark and invisible, full of potential but eternally silent. They would be there, but we could never see them with optical telescopes. Another possibility is that we are looking with the wrong eyes. Many dwarfs could be so diffuse, their stars so spread out, that they blend seamlessly into the background glow of the night sky or the cluster's own intracluster light. Our current surveys might simply be missing these ultra-faint ghosts, but the most profound possibility is that the deficiency is telling us something fundamental about dark matter's true nature. What if dark matter isn't cold after all? An alternative model proposes warm dark matter. In this scenario, the particles would have moved much faster in the early universe, possessing enough thermal energy to stream out of the smallest gravitational wells. This streaming effect would smooth out the cosmos on small scales, suppressing the formation of those tiniest dark matter halos from the very beginning. A universe built with warm dark matter would naturally have far fewer dwarf galaxies than the cold dark matter predictions. Hercules, with its notable lack of small satellites, becomes a critical piece of evidence in this high-stakes cosmological debate. Is the cluster's dwarf deficiency a result of astrophysical processes that stifle star formation, or is it a fingerprint of dark matter's intrinsic properties? A hint that the universe's hidden skeleton is warmer and smoother than we ever imagined. The answer lies in counting the faintest lights and weighing the deepest shadows. The dwarf census is a count of what we can see, but to weigh the cluster's true substance, we must learn to read the light that has been bent. Gravitational lensing is our most direct method for mapping the invisible, a cosmic cartography that uses distortion itself as its pen. It comes in two distinct forms, each revealing a different layer of truth. Strong gravitational lensing is the dramatic, rare event that produces those spectacular arcs and sometimes even multiple images of a single background galaxy. This occurs only when a background object lies almost perfectly behind the cluster's densest core, where the warping of space-time is most extreme. The resulting arcs are like celestial signposts screaming the location of the cluster's greatest mass concentrations. But they are only part of the story. Weak gravitational lensing is far more subtle and pervasive. Across the entire cluster, the shapes of thousands upon thousands of more distant background galaxies are minutely distorted. Their circular or elliptical forms are stretched into slightly elongated shapes, all preferentially aligned along the invisible contours of the cluster's gravitational field. No single galaxy shows a dramatic change. The signal is a statistical whisper across a vast population. By measuring the coherent, tiny distortions of perhaps tens of thousands of these faint background galaxies, astronomers can painstakingly reconstruct a two-dimensional map of the cluster's total mass, a map that includes everything: the shining galaxies, the hot gas, and most crucially, the dark matter halo. Specific studies targeting the Hercules Cluster have performed this meticulous work. Telescopes like the Hubble Space Telescope and ground-based observatories with wide-field cameras have stared for hours, gathering the faint light needed to measure these subtle shears. The resulting mass maps are revelatory. They show the luminous galaxies, the bright knots we easily see, are merely tracing the peaks of a much larger, much smoother mountain of dark matter. The dark matter forms a vast, roughly spherical halo that extends far beyond the visible galaxy population, its density gently tapering off into the cosmic void. These lensing maps have allowed scientists to weigh Hercules with unprecedented precision, confirming that dark matter outweighs normal matter by a factor of about 6 to 1. But the maps do more than just weigh. They reveal structure. They can show if the dark matter halo is smooth or clumpy, if it is perfectly centered on the cluster of galaxies or offset slightly, a possible sign of a recent disruptive merger. In Hercules, the lensing data has helped pinpoint the exact center of mass, often showing it aligns closely with the giant central galaxy and the peak of the hot X-ray gas, a sign of a relatively relaxed core despite its violent history. This invisible topography, charted by the bent paths of ancient light, is our most honest portrait of the cluster. It does not rely on assumptions about galaxy motions or gas temperatures. It simply shows where gravity is strongest. In the faint, stretched shapes of galaxies billions of light years behind Hercules, we find the undeniable signature of the shadow that builds the universe. Deep within the cluster's heart, a giant elliptical galaxy holds a secret engine. At its core, a supermassive black hole weighing billions of times our sun's mass is not sleeping. It is actively feeding, and its influence stretches far beyond its own event horizon. Observations from X-ray telescopes reveal a stunning structure in the hot gas surrounding this central galaxy. Two vast dark cavities, each spanning tens of thousands of light years, appear as symmetrical voids in the brilliant X-ray glow. These are not empty holes but bubbles, immense pockets of ultra-hot, magnetized plasma inflated by the black hole's powerful relativistic jets. The jets themselves act like cosmic blowtorches, drilling into the surrounding intracluster medium and pushing the gas aside to create these colossal, buoyant structures. You can see the bright, compressed rims of X-ray gas where the bubbles have shoved the surrounding material outward, like the wake of a ship frozen in a sea of million-degree plasma. This is the AGN feedback cycle in breathtaking action. The black hole's furious activity carves out these cavities, but that is only the beginning of the story. Once formed, the bubbles detach from the jets and begin to rise buoyantly through the cluster's hot atmosphere, much like a balloon of hot air ascends through our own sky. As they drift upward, they do crucial work. They stir the surrounding gas, creating turbulence and generating sound waves, ripples in the fabric of the hot plasma that travel outward for hundreds of thousands of light years. This turbulent motion and these waves transfer the black hole's colossal energy into the intracluster medium, effectively reheating it. This process is the precise counterbalance to the cooling flow. The gas wants to cool, condense, and rain into the center, but the rising bubbles and their associated waves pump energy back in, keeping the entire system hot and preventing that catastrophic deluge of cold fuel. It is a magnificent, self-regulating thermostat. The black hole's own feast provides the heat that prevents it from gorging itself into oblivion. Yet this elegant cycle hinges on a profound and unanswered question. What is the exact trigger that flips the black hole's switch from dormant to active? The prevailing theory suggests it is a specific rate of gas inflow. As a slow drizzle of cooling gas finally reaches the black hole's vicinity, it forms an accretion disk. Perhaps there is a critical threshold of density or inflow rate, a tipping point where the disk becomes unstable, igniting the jets. But is it that simple? Could it be that the trigger is more subtle, involving the buildup of magnetic fields within the disk to a breaking point? Or might external events, like a small galaxy falling into the core and disturbing the gas, provide the sudden buffet that wakes the giant? The timing is equally mysterious. Observations suggest these outbursts happen every few 100 million years, a rhythmic heartbeat for the cluster. How does the black hole know when to pulse again? This central engine, with its inflating bubbles and rising heat, is not just a local spectacle. It is the master regulator for the entire galactic metropolis, a single, violent object whose precise trigger mechanism holds the key to the cluster's long-term stability and the fate of every galaxy within its reach. That precise bubble-driven thermostat relies on measuring pressures and masses with extraordinary care. The Sunyaev-Zeldovich effect gives us one of the cleanest cosmic scales for that very purpose. It works because it is a direct imprint on the universe's oldest light. As the faint glow of the cosmic microwave background passes through the Hercules cluster, photons scatter off the energetic electrons in that million-degree intracluster gas. This interaction steals a tiny, specific amount of energy from the background radiation, leaving a distinct cold shadow in certain radio wavelengths. The beauty of this method is its simplicity. The depth of the shadow depends directly on the electron pressure, the product of how dense the gas is and how hot it is. This lets astronomers weigh the cluster without needing to know its distance, its age, or even see its galaxies clearly. It is a fundamental ruler, and because of this, the Sunyaev-Zeldovich effect has become an indispensable tool for discovering clusters across the vastness of the universe, especially the most distant ones that are too faint for optical telescopes to easily spot. Yet when scientists apply this pristine ruler to Hercules and compare its mass measurement to those from other methods, a subtle tension often appears. The Sunyaev-Zeldovich mass does not always perfectly match the mass calculated from the hot gas's X-ray temperature or from the exquisite distortions of gravitational lensing. This discrepancy is not a mere error bar, it is a potential clue buried in the cluster's complex physics. The Sunyaev-Zeldovich effect measures integrated pressure along our line of sight. Our standard models assume this pressure comes entirely from the random thermal motions of the hot gas, its heat, but what if the gas is not perfectly calm? Hercules, with its violent merger history, is likely filled with turbulence, sloshing motions, and powerful magnetic fields. These dynamic forces provide something called non-thermal pressure support. Think of it like this: if you try to weigh a pot of boiling water by measuring the pressure at the lid, you would get an accurate reading if the water were still. But if the water is churning violently, the pressure fluctuates and your measurement might be off. The turbulence and magnetic fields in the cluster's gas act like that churning, adding an extra component of pressure that is not simply due to heat. This non-thermal pressure can make the gas appear puffier and more supported than our thermal models predict, leading the Sunyaev-Zeldovich effect to infer a slightly higher total mass than the X-ray temperature, which is sensitive primarily to the thermal state, might suggest. Resolving this tension is not just an academic exercise, it is vital for cosmology itself. Clusters like Hercules are used as standard candles to measure the expansion history of the universe and the amounts of dark matter and dark energy. If we do not perfectly understand the physics inside them, if we cannot accurately convert what we observe into a true mass, then our measurements of the cosmos itself become blurred. The discrepancy in Hercules forces us to refine our models. We must account for the whirlpools and magnetic storms left over from its cataclysmic formation. It reminds us that these cosmic cities are not simple, relaxed spheres of hot gas, but dynamic and messy systems. Each mismatch between our different weighing scales is an invitation to look deeper, to listen more carefully to the whispers of ancient light, and to calibrate our understanding of the universe against the stubborn, complex truth of a single, magnificent cluster. The state of a cluster's heart is written in X-ray light, a thermal fingerprint of its past. To read this history, astronomers turn their most powerful X-ray telescopes, like Chandra and XMM Newton, toward the Hercules cluster. They do not simply take a picture, they perform a spectroscopic autopsy. By breaking the X-ray glow into its constituent energies, they can map both the temperature and the density of that million-degree intracluster gas with extraordinary precision. In a truly relaxed, ancient cluster, the gas tells a predictable story. At the outer edges, it is hot but relatively thin. As you move inward toward the gravitational center, the gas becomes denser and crucially cooler. This is the classic cool core profile, a smooth, steep gradient where the dense central gas has had billions of years to settle, radiate its heat away, and pool at the cluster's heart. The X-ray map shows a bright, sharply peaked core of intense emission, the signature of a mature, undisturbed system that has not suffered a major collision since its formation. Hercules presents a more complicated and more intriguing portrait. The X-ray observations reveal a core that is far from serene. Instead of a smooth, steep temperature drop, the gradient is shallow. The gas remains hot and disturbed all the way into the very center. The brightness profile is flatter, not sharply peaked, and the map often shows subtle clumps and asymmetries like eddies in a cosmic river. This is the hallmark of a non-cool core, or what some call a warm core. The gas appears thoroughly stirred, as if a giant spoon has churned the entire central region, redistributing the heat and preventing a dense, cool pool from forming. This single piece of thermal evidence points decisively toward a violent recent history. The most compelling explanation is that Hercules experienced a major merger, a collision between two massive subclusters within the last few billion years. That cataclysmic event would have sent powerful shock waves and turbulent sloshing motions through the core gas, mixing the hot and slightly cooler layers together and erasing any pre-existing cool core. The cluster has simply not had enough time to relax, re-establish a calm central gradient, and regrow a cool core from scratch. Determining the exact state of Hercules' core is more than a classification exercise. It is a direct measurement of the cluster's dynamical age. Is this a settled elder or a turbulent adolescent? The evidence leans heavily toward youth. The disturbed, warm core suggests we are witnessing Hercules not long after its most defining traumatic event. The fact that the gas is still so thoroughly mixed means the echoes of that merger are still ringing through the system. This has cascading implications for everything else we observe. It explains why the radio halo is so prominent as the merger's turbulence continues to energize particles. It contextualizes the bent jets and high-velocity galaxies as the gravitational potential is likely still settling. It even informs the dwarf galaxy deficiency, as a recent merger would have been a particularly efficient period of destruction and stripping. The cool core controversy in Hercules is ultimately a debate about timing. By reading the temperature of this ancient gas, we are essentially taking the cluster's pulse, and the rhythm we find is not a slow, steady beat, but the rapid, fading heartbeat of a colossal impact, a defining moment of violence that continues to shape every aspect of this galactic metropolis today. From its invisible dark matter skeleton to the faint glow of exiled stars, the Hercules Cluster reveals a cosmos in constant, dramatic flux. We have journeyed through 25 of its deepest enigmas, each a window into the forces that build our universe. This is not a serene museum of distant lights, but a living, breathing, and often violent ecosystem. Galaxies are stripped and transformed, black holes regulate an entire metropolis, and colossal shock waves from ancient collisions still echo across millions of light years. Every unanswered question, from the missing dwarf galaxies to the precise trigger of the central black hole's heartbeat, is not a dead end but a frontier. These mysteries are the engines of discovery, pushing our telescopes and simulations to their limits, forcing us to rewrite our understanding of gravity, matter, and cosmic evolution. The Hercules Cluster teaches us that the universe is far stranger and more dynamic than we ever imagined from our quiet galactic suburb. So, which of these phenomena captured your imagination the most? Was it the ghostly ultra-diffuse galaxies, the bent jets, or the fossilized radio relics? Let us know in the comments below, and if you enjoyed this deep dive into cosmic mysteries, be sure to subscribe. Our universe is filled with enigmas waiting to be explored.